Hello there everyone. Today I thought we'd do an exam paper walkthrough of the Physics Paper 1 from 2018. I've got both the foundation and the higher here. If you didn't know, that actually the back half of the foundation paper, starting here at question 5, actually question 6, is actually the exact same as the start of the higher paper. So if you're a higher student wanting to look through this, I'll put a timestamp in for when the higher questions start, and for the foundation I'll tell you when those foundation questions stop. But let's get into it. Okay, so looking at question 1, it says that there are many energy resources. Which two energy resources are renewable? Now, looking at that, the key word here is obviously renewable. Okay, and that means that the energy is replaced. Energy source is replaced as quickly as it's used. Okay, so coal is obviously dug up out of the ground. There's no easy way to quickly remake that coal, so it's not going to be replaced as quickly as it is used. However, biofuel, which is a fuel made from plants that are grown, or even like cow pats, these you can obviously grow more crops and make more fuel. Gas, really we're thinking here of natural gas. This is dug up and piped up and mined. It's a fossil fuel. It is not renewable. Geothermal, however, is. Okay, geothermal is where you pump down water to hot rocks in the Earth's crust. This turns the water into steam, goes up and turns a turbine. So those are our two renewable energy resources. Okay, question 1.2 says that some non-renewable energy resources are more reliable than others. Which statement correctly describes a reliable resource? And I often get asked this actually when people say, well, why do we bother with fossil fuels? Okay, the reason we bother with fossil fuels is because they are really cheap. Okay, at the moment, renewable resources are actually getting cheaper. But crucially, they are reliable. Okay, and that's because you do not need certain conditions for them to be able to generate electricity. A solar panel will only work if there's sun out. It doesn't work at night. A wind turbine will only work if it's windy. Whereas coal and gas and nuclear fuel and oil will work no matter the conditions. So this means that they're really reliable. So when it says which statement correctly describes a reliable resource, okay, we really mean that it is predictable. We know that it's going to be generating electricity. Going over here to question 1.3, we see here a wind farm. Okay, it says the total power output of the wind farm is 19.6 megawatts. All of the wind turbines have the same power output. What is the power output of one wind turbine? Okay, so we see here this whole farm is 19.6, but we have crucially got 1, 2, 3, 4, 5, 6, 7 wind turbines. So if 7 wind turbines are generating 19.6, that means that one wind turbine will be 19.6 divided by 7. Okay, and I can put that into a calculator. You can always use a calculator in the exam, but let's go old school. See how badly my skills have rusted. Okay, 2.8. So that means that one wind turbine has an output of 2.8 megawatts. Okay, give two reasons why people might not like having wind turbines near their homes. And that's actually quite weird because I actually think wind turbines look really cool. But if you've ever been near a wind turbine, they're actually really noisy. So you get what we call noise pollution. Okay, because they're noisy, and we get visual pollution. Okay, this is where people say they don't look nice. There are a couple of other reasons here, and I'm sure that you will have some good suggestions. But the key thing here is that you actually read the question and you're thinking about might not. Okay, you don't say because they're renewable or anything like that. Okay. So looking at question 1.5, okay, we see that it's looking at the way that electricity is generated in the UK. The total amount of electricity generated was the same in 2015 and 2014, so that means that the kind of size of the pie charts are the same. But what we're really looking at here is the distribution. So we can see here we've got a big slice of coal, nuclear, gas, renewables is 19% and other fuels is 2%. And here we've got a similar but clearly different picture. There are changes in the amount of different energy resources used between 2014 and 15. Explain the environmental impacts of the changes. So this is really kind of a twofold. The key word here is explain. And if you put up with me in class, I always like to talk about Rustman, okay, a way to answer these longer questions. I crucially want to read the question, which is what I've done there. I want to underline the command word, which is what I've had a look at here. The key thing with explain is that I actually need to give a reason. Okay, I can't just state something. Now I'm going to look at subject words. These are key words which I'm going to have to factor into my answer. Okay, so to me that really is environmental impact. Okay, we've got to be thinking about how these affect the environment. Energy resources can also be considered in that way. And then I suppose all of the various different types of energy. Think of any other keywords. Okay, so to me this question really is not going to be complete unless I mention fossil fuels, which can then mean that I'm talking about carbon dioxide, which could also mean I'm talking about greenhouse gases. Okay, there might be some other ones which come up. Make sure you organise your answer. Okay, this means I have a logical progression. Whenever I see people answer long answer questions, they tend to be like a big blob of text. Use paragraphs. When you're making a point, start a new line, make it really clear to the examiner. I want to make sure that I answer all of the question. Okay, now this is actually quite a straightforward question where there's just one part here, but often, we might see this later on, there might be different parts. And then afterwards we're going to make sure that we go back and we read our answer to see it makes sense. So let's have a go. So looking here, I can see that coal has gone down. Okay, gas has stayed the same, renewables have gone up. Okay, we don't know what type of renewables, but that's clearly gone up. Nuclear, about the same, maybe gone up a smidge. Okay, so I'm going to start looking at the coal question. So between 2014 and 2015, okay, coal generation decreased, and it's always good to use some figures if you've got them. So 30% to 22%. Okay, and now I'm going to weave in those keywords I looked at the bottom, as coal is a fossil fuel. Okay, it releases carbon dioxide through combustion. this carbon dioxide can cause global warming through the greenhouse effect. So that's my key points there looking at coal. So the next thing that I'm going to look at, I'm going to start on a new paragraph just to give my answer a bit of clarity. You have to remember that the examiners are going to be marking these, and they have quite a lot of exams to mark. So you want to make it as clear cut to them that you actually know what you're talking about. Even if you don't. I don't half the time, I make it up as I go along. So I think the other key one here to look at is renewables. So also renewables increased. And again, if you can supply a fact, do it. 19% to 25%. Okay. So let's think about what the environmental impact of using more renewables will be. Well, they're overwhelmingly positive. There can be some renewable energy resources which are negative when you think about dams, okay? But if you are using renewables, you are crucially not generating greenhouse gases. Okay, so these do not generate greenhouse gases, and so do not contribute overwhelming environmental damage. Okay, so it's not a perfect answer, but we can see there that for 4 marks I've made 2 points and explained it twice. Okay, crucially doing the explain. Okay, moving on to question 2. We've got here a battery pack connected to a phone, quite an old phone I think, probably for this. Looks like an HTC. And the question says, why does the battery in the phone need recharging? Okay, the big thing here about batteries is that everyone seems to think that they are stores of electrical energy. Okay, they are not. Okay, inside a battery you have got different metals and an electrolyte between them. A chemical reaction happens and that generates the electrical energy. It converts some of the energy to electrical energy, would be better to say. So batteries are not a store of electrical energy, okay, they are actually a store of chemical energy, which is inside the battery, okay, and if I'm doing an energy transfer diagram, battery, and out of that comes electrical. So the question is saying, what type of energy are they? Chemical. Okay. The power source provides a current of 1.86 amps, a potential difference of 3.90 volts. Calculate the power of the power source. Use the equation power equals potential difference times current. Now, in the foundation side, you will see that you probably get given the equation. Okay, towards the higher, you won't, or you might have to rearrange it. Now, again, similar to Russman, I have a scheme to always answer these types of questions, and it's funky. Okay, loads of you I know like to annoy me and pronounce it as fancy. I'm going to rise above it. So I like to write the formula, and then I'm going to check that the units are okay, put the numbers in, calculate the answer, and then don't forget the units at the end. You can see here that this was nice, and then I try to make it into a word. Enjoy that. So looking at the question, the first step I'm going to do is the formula. Now we're lucky because it actually gets given to us here, but I'm still going to write it out. I really can't emphasize enough that if you follow this logically, you will get the marks for the question, or crucially, if you muck up at any point, you will get the marks up to that point. So The formula is power equals potential difference times current. Remember, scientists are a bit weird, so power is P, nice and straightforward. Potential difference is V, okay, because remember that is also a word for volts or voltage, okay, and times current. Now this is where the scientists really lost it, and they decided that current would be I. It technically stands for induced current, but like, why would you use I for current? It's just being annoying. I'm now going to check the units. Are they in the standard units of that measurement? So potential difference is measured in volts, and you can see here that it is in volts, so we're happy there. I is current, and that is measured in amps, and you can see here, okay, that it is measured in amps, so that's fine. So we've done our units check. Next is the numbers in, so I'm going to write this again, okay, but putting in the numbers for the values that I want. So instead of V, I'm going to write 3.90 because that is the potential difference. I, the current, you can see here is 1.86. So I'm going to make that 1.86. That's my numbers in. The next step is to calculate it. Okay, again, you can always use a calculator. All right, there is no non-calculator science paper. Okay, I'm going to use Siri. Hey Siri, what's 3.90 times 1.86?
3.9 times 1.86 is 7.254.
Thank you. Oh, I actually forgot it. That's shocking, isn't it? I was too busy trying to be nice to Siri. Hey Siri, what's 3.9 times 1.86?
3.9 times 1.86 is 7.254.
Thank you. Always be polite, even if it's a phone. Now, for this one, I'm given it's also the foundation paper. I'll just leave it as that. I don't want to see people writing all the numbers from the calculator in there. Don't be afraid to round it, but I'm going to leave it as that because it's just about okay. Technically, I could probably put it to 3 significant figures, but that's my answer. Don't be afraid to use a calculator. Obviously, you can't use Siri in the exam. Things will be easy. Last thing is don't forget the units. Now, actually, this is part of the question. It says choose the correct unit from the box. So it's really asking you, what are the units of power? And hopefully you can recall that the units of power are watts, and they have the symbol W. Okay, so that would actually equal 7.254 watts, and that would be my answer. I'm going to really emphasise it by writing it in the boxes that they asked for, so the power is 7.254 and the units are watts. Okay, notice how by following this logical progression we got the answer and everything was quite nice. Okay, continuing with the battery pack, you can see here they've got 3 battery packs. They've got compact, large and high capacity, and we've got some data about them, and it says the student chose the large power source. So the student said this is the one, okay, and it says why did they do that. I've set this question in lessons quite a few times, and actually people find this quite hard because what happens is when you've got a table of data, people tend to just straight up compare them, and that's not enough. Okay, if you've got a table of data, do something with it. Okay, that means do a calculation. Don't just regurgitate the info. Okay, so don't just say, well, large has got 5 times the charges, so it's going to be better. All right, do something with it. So here, let's have a look at this. Compact weighs 100 grams and you get 1 charge. Okay, so if you think about it, that's I'm going to use this space over here. Compact is 100 grams per charge, right? Each charge takes up 100 grams of battery. Here, I've got 5 charges, 5 times the charge, but it's 200 grams is what it weighs. So that means the large is 200 for every 5 charges, which means it's 40 grams per charge. The high capacity, I've got 600 grams and 10 charges. Okay, so 600 grams for 10 charges, and hopefully you'll see that that is 60 grams per charge. And this might actually then reveal to us why the student picked the one that he did, because, or they did, it's a bit presumptuous of me, because the compact is 100 grams per charge, large is 40 grams per charge, and the high is 60 grams per charge. That means that it is the most, it's got the highest or the lowest weight to charge ratio, which is what you want, because you don't want to be carrying around a really heavy thing and not get the beef from it. If you think about it, it'd actually weigh less to have two large battery packs than it would to have one high capacity. So, suggest why the student chose the large power source. I'm going to use those calculations that I made in my answer. Okay. So we can calculate a power to weight ratio for the compact. Is 100 grams per charge. Then, because I'm going to build up to a nice crescendo and say why they picked large, the high capacity is 60 grams per charge. The large capacity has the lowest, so I'm now saying why this one is the best. Weight per charge at 40 grams per charge. This means that you carry less weight for your charges, and so the student chose it. Okay, moving on to the next question. We've got a skateboarder on a ramp. We see that the ramp is 4 meters off the ground. And we also see here that the girl has a mass of 50 kilograms. The first question says, calculate the gravitational potential energy, GPE, of the girl at the top of the ramp, and using the equation. So again, it's an equation question, so it's time for funky. Okay, you know, again, we've actually got the equation given to us. We might need to remember this if we're higher on the higher paper. The formula says GPE equals mass times gravitational field strength times height. So I'm going to say that the formula is GPE equals mass m, gravitational field strength g, height h. Okay, units check. Got to check that all of my numbers are in the correct units for those values. So height is measured in meters. Excellent, it's in meters. Gravitational field strength, they actually say that they don't muck about with the unit in the paper, but just worth a check. Newtons per kilogram. There are a couple of different variants of that unit, so just be aware. Mass is in kilograms, not grams, it's in kilograms, and you can see here that the mass of the girl is at 50 kilograms, so that's fine, that's in our units. So that's our units check done. Time to put our numbers in. So I'm going to write it again. The mass is 50. The gravitational field strength is 9.8. And the height is 4. Okay, so now work it out. Again, don't be afraid to use a calculator. I'm going to consult Siri. Hey Siri, what's 50 times 9.8 times 4?
50 times 9.8 times 4 is 1,960.
Thank you. She just ignores me. It's a very one-way relationship. Okay, so that's excellent. That's our calculation. Then we don't forget our units. So this is an energy. Whenever you see the word energy, think about joules. Okay, so the units for this is joules, and actually we get given it, but it's still a good habit to keep in like that, and that is our answer. So again, I'm going to write it there just to make it extra clear. Okay, the next one says the girl has a speed of 7 meters per second at the bottom of the ramp. Calculate the kinetic energy of the girl at the bottom of the ramp. And again, it gives us the equation. Now, we've got to think about this now. And very often, if you've calculated something in the first part of the question, it's going to come into play in the second part of the question. That's not an exhaustive rule, but it might be worth bearing in mind. So if we think about this equation, at the moment I don't know the kinetic energy. 0.5 is just a number, I've got that already. The mass is still 50. I'm actually going to write these in just for clarity. 50 kilograms. The speed I get given. Okay. Speed is 7 meters per second. So actually I don't need this question. But I might need it a little bit later on. Okay, actually I'll need it in the next question. So, using our rule again, the formula, okay, F is kinetic energy, KE, equals half 0.5 times m for mass, and speed, I'm going to put as v for velocity, because if I square it anyway, it doesn't actually matter the direction. I'm then going to put the numbers in. So half is already a number, so that just carries on. M, the mass, we've established is 50. V, the speed, is 7. Okay. I sometimes like the big problem which people run into with kinetic energy equations is to forget to square it. So therefore I always add in an extra step where I do the squaring first, so it just avoids the problem. So it's half times 50 times 7 squared is 49. And then again I can ask my Siri, hey Siri, what's half times 50 times 49?
0.5 times 50 times 49 is 1,225.
Thank you. So again, don't ever be afraid to use a calculator. So that's my answer, and you can see I've already leapt ahead and put the units there. So our kinetic energy is 1,225 joules. Right. The next question says not all of the GPE has transferred in kinetic energy. So we started off with 1,960 joules of GPE, and that has transferred into 1,225 joules of kinetic energy. So we've got two statements here to explain why that is the case. Now, whenever there's an energy transfer, some energy is wasted. Okay, you can never get a higher output than an input, and pretty much I think the only example which comes to my mind where it's a perfect energy transfer is matter colliding with antimatter, and I don't think they're going to be asking about that at GCSE. So some energy is wasted. We can think about what that is wasted into. We get heat, we'll get sound, things like this. These are all things which are transferred to the surroundings. Okay, mass of the girl too low, doesn't make any sense. The ramp's not high enough. High enough for what? They're trying to do a special trick. It's not what the question's asking. The GP of the girl is not 0. That is the correct second option. We can think about why. If I look back at the diagram, you can see here that the ramp doesn't touch the floor. Okay, that means that there is still a height. So the GPE of the girl here at the bottom of the ramp is actually not 0, because it would be 0 here on the ground. Okay, so this means this height here means that the GPE of the girl is not 0 because they're not actually at the floor. Explain how lubricating the wheels of the skateboard can increase the speed of the girl. Use the ideas about energy in your explanation. Okay, so we've already said that this is an energy transfer, and the key thing here is conservation of energy. Okay, this means that energy cannot be created, it cannot be destroyed, only transferred. So I think about what the transfer is going on here. Well, I've got GPE going to kinetic energy. Okay, but also I'm going to get some heat and some sound. That's actually going to be tiny compared to this one. This one is our big waste. And we think about how is heat generated? Well, it's generated with friction. If you rub your hands together and you really push in, you start to feel that heat transfer to your hands. Okay, that's why on a cold day you do rub your hands. So how can we combat friction? Well, that's where the lubrication of the wheels comes in. So notice how I've started by what I know and I've made a logical argument, and the answer is essentially walking that logical argument back. Most science questions are just simply making a point and then following it through with logical explanation. So lubricating the wheels, okay, will reduce friction. That's point one. Less friction means less energy wasted as heat. That's Mark 2. Mark 3, this means more energy is transferred to kinetic energy. Okay, kinetic energy, remember, is the energy of movement. And if I want to go faster, I want that to be as big as possible. This means more energy is going to transfer to kinetic energy, meaning the girl moves faster. And there's my marks. Okay, next question. Some ceiling lights in the home are connected to the mains through a 2-core cable. Most of the wires in your home are actually 3-core. If we think to the when you've had to wire a plug in lessons, or you might have seen a dodgy wire in your home. But this is a 2-core cable, so we know that that is not typical. It suggests why some ceiling lights do not have an earth wire. Okay, so to understand that, we're going to have to think about what an earth wire does. Now this is the one overwhelmingly, I'm going to draw it down here, overwhelmingly for safety. What that means is if I take like a toaster, it's going to be the world's worst drawing of a toaster. Oh, it looks like a tortured cartoon. Anyway, toasters tend to have like a metal case, and say there was a problem in the wiring and the electricity, the wires touched the case, then that means that if I touch that case, I'm going to get a shock. So what we do is we have a wire here, which is my earth wire, which if the live wire is touching the metal case, it provides a return route back to earth. Okay, hence what's called the earth wire. Actually, if you walk about, you might see on the ground these pavement slabs look like this, where they'll say earth rod, and it's literally just a rod of copper shoved into the earth, where if there's something electrically wrong, all of the wires link up to this rod, and it means that the electricity goes into the ground. Okay, you might have heard of a lightning conductor, which does the same thing. All it is a way where the electricity can safely return to the ground, rather than go through you. Because if that happens, that's not good. So why do we need an earth wire? Well, if we're going to touch something where something can be go electrically wrong, then I need that safety. Well, here it's on a ceiling light. Now, I am quite tall, but I don't really go around touching my ceiling lights. Okay, so that's going to be the base of the argument. Because I'm not going to be touching it, okay, it doesn't need a safe return to the earth. Okay, so because the lights are on the ceiling, the case cannot be easily touched, and therefore doesn't pose a risk of electrocution, therefore no earth wire needed. Okay, write down the equation that links charge, flow, current and time. So we are now being asked to remember an equation. Now again, this is where if you are really stuck, just put an equal sign and a time sign there, and you might be right. Okay, you know, most of the time you'll be correct, and actually this is one where that is the case. I would suggest you go away and learn them, because it's something you have a control over, is learning the 23 equations. So it's the easiest thing is just to write the words. You can try the symbols if you like, but let's write the words first. So the equation is charge equals current times time. So our lucky trick actually here is correct. That is just the equation. In terms of symbols, this is another one where scientists went weird. Okay, charge has the symbol Q, current is I, as we've said before, and time is T. That one's not too bad, is it? Okay. The next question then says there is a current of 2.95 amps in one of the copper wires for 60 seconds, sorry. You calculate the charge flow through the wire, use your equation from question 4.2. Now, because it says use your equation from question 4.2, even if you get this wrong, as long as you use that equation, you can get the marks. So don't be afraid if you're not sure about that. That doesn't block you out from the rest of the question. So again, we're doing an equation. Outcome's funky. So I'm going to write the formula. Q equals IT, or I times T, just to make it clearer for you. That's my formula. Units check. That's in amps. Fine. That's in seconds. Fine. Numbers in. The current is 2.95 amps. So instead of I, I'm writing 2.95. The time is 60 seconds. Okay. Calculate. That will be 180 minus 3, which will be 177. Didn't need Siri for that one. That's my calculate. Again, use a calculator. Why you don't forget the units? Well, in this question, the units are of charge, and charge is measured in C, coulombs. Okay. That's the unit of charge, and you can see actually it's given to us here anyway. So there's our answer. Charge flow equals 177 coulombs. Okay, so figure 7 shows a potential difference graph for a piece of copper wire. Draw another line on figure 7 for a wire with a different resistance. hopefully you might vaguely remember your teacher or me talking about this, a straight line meaning that it obeys Ohm's law, or that this is an ohmic resistor. Okay. Current, if you think about it, it means flow. How many electrons are, or how much charge is flowing through the wire per second. Potential difference I like to think about as the oomph through the circuit. Okay, how much of a push are those electrons getting to go through the wire? So if I want to have a different resistance, okay, for argument's sake, let's take a higher resistance. That means for a bigger oomph, for a set oomph, I'm going to get less current going through. Okay, so that means that this wire here, okay, actually, to really emphasise that fact, I'm going to use a ruler. Okay, this wire here does actually have a higher resistance. Okay, now they will always go through the origin, because if you think about it, if there is no push, then there is going to be no flow. Okay, so at zero current there is zero resistance. If you work in a mathematical way, the equation is V equals IR, so if this is 0, then R must be 0 and I must be 0, or one of them must be. So yeah, if I'm going for a lower resistance, then that line would suffice, because I'm getting more flow, or more electrons going past for kind of less oomph. I don't have to give it as much beams to go through. So the 2 marks there for actually will be for A, straight line through the origin, and B, the second mark will be for having a different gradient, a different slope. So that's how we get the marks on that question. Moving on. Some fuses have a thin piece of copper that melts if the current is too large. Draw the circuit symbol for a fuse. There's no way around it, you just need to remember it. It's quite easy to confuse. This is the symbol for a resistor. Okay, lots of people I see write that. Okay, the key thing here is it's got a thin piece of copper that melts. If you actually see a fuse, it is a glass tube with a thin piece of wire through it, and that's what the symbol is. Okay, it is that with a thin piece of copper through there that melts. That is the fuse symbol. Describe how the movement of copper particles in the wire changes when the copper melts. Okay, so this is now pivoting from an electricity question to a particles question. This is really talking about your solids, your liquids, and your gases. So in a solid, you have the particles arranged in rigid rows. The particles vibrate a little bit, and they've got strong forces between them. In a liquid, okay, they're still quite close together. I think people misunderestimate that. But they can move about past each other, okay? Whereas in a gas, they're all over the place, zipping about. Okay, so describe how the movement of the particles in the wire changes when the copper melts. What the question is really asking is how do the particles change from a solid to a liquid? Okay, so in the copper wire, okay, the particles form a tight, rigid structure. They do not move, only vibrate, and have high forces between them. Notice how I started a new paragraph there because I'm making a new point. In a liquid, the particles can move freely. Okay, that's our key difference there. So next thing, old copper wires are melted when they are recycled. Calculate the energy needed to melt 500 kilograms of copper at its melting point. Specific latent heat of fusion of copper equals this. Use the physics equation sheet. Whenever you see that, the equation will be on there. Okay, if it doesn't say that, you don't need the sheet. Alright, I see so many times where people, like the previous question here, where they'll just pick a question off the equation sheet. Luckily, I have the insert with me here. Okay, these are the 7 equations that you get asked to be familiar with, but not necessarily know off heart. Okay, they get given to you. So look for the words that is mentioned in the question. Energy. Okay, 500 kilograms means I'm going to be looking for mass. Specific latent heat of fusion. Alright, so let's have a look here. What do I see? Thermal energy for a change in state equals mass times specific latent heat. Specific latent heat, excellent. So I'm going to be wanting to use this equation. So I'm going to, again, follow my favourite, which is funky. Okay, F formula, it's E equals ml. E equals m times L. So units check. Mass is in kilograms, that's fine. Specific latent heat of fusion, they're not going to mess with. Okay, it's too complicated a concept really to talk about. Actually, whilst I say that, I'm wrong. If you have a look here, ignore me, that's shocking. If you have a look here, it says 200 kilojoules per kilogram, and you can spot here in the answer that it wants it in joules. Okay, so this is the first time where we've had to confront the U in funky, the units check. Okay, so 200 kilojoules per kilogram. Now, if you're playing like games or whatever, okay, hopefully you remember that K means 1,000, right? People often say, oh, like 3K, well, that means like £3,000 or whatever. So it's no different in science. 200 kilojoules means 200k, right? 200k will be 200,000, so it'll be 200,000 joules per kilogram. So I have now done a unit conversion. C, calculate, put the numbers in. So energy equals M, mass 500 times L, which is 200,000. Calculate, so 500 times 200,000. Okay, yeah, it's going to be 1, 2, 3, 4, 5, 6, 7. Okay, again, check on the calculator. Even though I did that in my head, I'm going to check. Alexa, wrong phone. I'm talking to all the technology. Hey Siri, what is 500 times 200,000?
500 times 200,000 is 100 million.
Excellent. Okay, why, you don't forget the units, joules. So that would be 100 million. Now that is a massive number, but if you think about it, it makes sense, right? It's going to take a lot of energy to melt half a ton of copper. Alright, that's going to take a lot. Okay, next question. 5. Radioactive nuclei can emit alpha, beta and or gamma radiation. Which type of radiation is the most penetrating? Okay, so I'm going to try and take all these at the same time. Really, let's think about what alpha, beta and gamma are. Okay, so alpha is a helium nucleus. Okay, it's 2 protons, 2 neutrons. Beta is an electron, and gamma is an electromagnetic wave. So if I look at the mass, okay, this has a mass of 4 because it's 2 protons, 2 neutrons. Beta is an electron, so it's very small. It's not 0. it's about that. Actually, we'll make it 1800. It's very small, is the point. Gamma has a mass of 0. Light doesn't weigh anything. So I always like to think about this. I played rugby when I was younger, so I like to think about these as people running towards me, right? So alpha, right, is a big lad coming towards me, big mass. That means that if he hits me, it's going to hurt, right? If you have a big person run into you, it's going to hurt, right? So penetration power is it's how easily they get through, and ionization energy, ionizing power, is how much oomph they have. So alpha, mass of 4, big person running towards you, that means if it hits you it hurts. So the ionizing is high, because if they hit you, right, if you're an atom, they're going to knock electrons off. Big punch. Beta much weighs less. Okay, so if they hit you, it's not going to hurt as much. And gamma, they weigh nothing. All right, it's like a little, like a little 2-year-old child running into you. So that's going to be low. Penetration basically means how far are they going to be able to go. Right now, this big person who's going to hit into you and it's going to hurt, they're probably going to be running out of breath quite easily. All right, so alpha radiation is actually got a low penetration power. So it's actually easily stopped by paper, by air, by your skin. Right? So that's really dangerous if you breathe it in, or you it's contaminated on some food and you eat it, because once it's inside you, then it's going to be doing the high damage. But actually it's stopped on the surface most of the time. Beta, again, it's a bit of that compromise. And gamma, it weighs nothing, right? It's got nothing to weigh it down. It just whizzes about all over the place. Really high penetration. Okay, so beta, we tend to talk about it being stopped by aluminium, and gamma technically is never stopped, but can be reduced significantly with lead. So using those things that we've talked about, probably quite confusingly, I have done a podcast on it, so look it up on the channel. What one is most penetrating? Well, gamma is the most penetrating because it weighs very little, so it can go through things quite easily. Right, it's like a ghost, right? Which type of radiation is most ionizing? Well, that's alpha because it weighs a lot. So as soon as it hits an atom, it's probably going to be knocking electrons off and causing problems. What type of radiation has the longest range in air? Well, that's another way of asking what is the most penetrating, right? What one is going to be least likely to interact with the air and is going to travel furthest? So that is going to be your gamma. Okay. When radioactive isotopes in the Earth's crust decay, they release energy. The decay causes the heating of rocks in the crust. And you can see here I've got this decay equation. Complete table 2 to show the numbers of neutrons and protons in the nuclei. So what this is really asking you is, do you know what these numbers mean? Okay, the top number is what we call the mass number, and the bottom number is what we call the atomic number. Now what do they mean? Well, the atomic number is the number of protons in the nucleus, and the mass number is the number of protons and the number of neutrons. Because if you remember the weights or masses of the particles, protons weigh 1, neutrons weigh 1, and electrons are so small we don't worry about them. So if I'm weighing an atom, I'm basically weighing how many protons and neutrons there are. So if I look at the example here, it says uranium 238. Well, number of protons is actually the easiest one because it's the number at the bottom, the atomic number, and that is going to be 92. Thorium, I don't know the number of neutrons, but hang on, it's got the mass number of 238. So I know there are 238 protons and neutrons, but I also notice that bottom number that there are 90 protons. So of that 234, 90 of them are protons, so that means it's going to be 234 minus 90, which is going to be 144. Okay, the next question says, geothermal power stations pump water through heated rocks. The temperature of the water increases from 20 degrees C to its boiling point of 100. Calculate the change in thermal energy when the mass of water heated is 150 kilograms. Specific heat capacity equals that, and use the physics equation sheet. So again, whenever I see use the physics equation sheet, out comes the physics equation sheet. Only then do we use it. We're talking here about specific heat capacity, and again that comes up here, so I'm after this equation. So again, let's involve a bit of funky. So the formula I'm going to use is change in energy equals mass times specific heat capacity times change in temperature. That symbol there you've probably seen in maths, it's theta, the Greek letter T, so don't get overly confused. That's T. I'm actually going to write it as T just to make it even more clear. So the change in energy, also the triangles mean change, alright? So the triangle is the Greek letter delta, and that's for change. So triangle E, or delta E, means change in energy equals mass M times C, specific heat capacity, times delta, or triangle, theta. Okay, so change in temperature. Alright, that's our formula. Units check. Well, this one's, we've got a little bit something different to do here because it's a temperature change. So if it starts from 20 and goes to 100, that means that the temperature change is actually going to be 80 because it's gone from 20 to 100. If I'm checking the other units, that's in kilograms, that's fine, and the specific heat capacity is in joules, that joules per kilogram, degree C, that's fine. So N, numbers in, I'm going to put them in. So change in energy equals M mass, so I've got 150 kilograms of water. C, specific heat capacity given to me there is 4,200, and the change in temperature is 80. C, calculate. Again, use a calculator. Hey Siri, what's 150 times 4,200 times 80?
150 times 4,200 times 80 is 50,400,000.
Thank you. So that's calculated it, and finally, why you don't forget the units. Excellent. Specific heat capacity is probably, I think, one of the hardest equations that you'll have to cover at GCSE. The only other harder equation questions are when it involves two different equations in the same question, or three equations in the same question. But apart from that, I would say the straight up raw, you've just got one equation, I would say that that's the hardest. So if you can do that, well done. Okay, so now we're reaching the questions which are on the higher paper. Okay, so I'm going to change colour. We're going to go green. Okay, so these are going to be the common questions, the questions which are on both the higher and foundation. Okay, so figure 9 shows two models of the atom. I've got the plum pudding and I've got the nuclear model. Okay, write the labels on. So this negative particle here is the electron. If you remember, a plum pudding says that there are negative electrons in an atom of positive charge. So this kind of whole circle, whole particle here is the atom. The nuclear model, the key difference here is that it has a nucleus, right? This is what Rutherford discovers. Well, actually, he got his PhD students to do it for him and then took all the credit for it. So that's fun. So the nuclear model, clearly this middle part is important. That's the new thing. That is the nucleus. Okay. And the key difference here is we're saying that here we've got a vague area of positive charge, whereas here the positive charge is really concentrated in that middle. And that explained, if you remember, the gold foil experiment, where the electrons, where they fired alpha particles at the atoms. Here there's nothing to stop it, whereas here they've got a nucleus which can kind of do these big deflections out of the way. These loops here are the orbits of the electrons. We also talk about them as being shells, okay, because that nuclear model was developed by Niels Bohr. Explain why the total positive charge in every atom of an element is always the same. Okay, so clearly we need to think here about elements, okay, and the positive charge. So how do we define an element? Okay, an element is defined by its proton or atomic number. Okay, so an element always has the same atomic number. So if they think about what that means, if they've got the same atomic number, okay, this means it has the same number of protons. We talked over here about how the atomic number is the number of protons. Protons are positive. They are the particle, the subatomic particle, which is positive. So each element has the same positive charge. Okay, question 6.3. The result from the alpha particle scattering experiment led to the nuclear model, which I just talked about. Alpha particles were fired at a thin film of gold at a speed of 7% the speed of light. Determine the speed of the alpha particles. So the speed of light is 300 million meters per second, and it says it's 7%. So the question is really asking, what is 7% of 300 million? Okay, easiest way to do that. Some people like to take 10%, halve it, and go down to like 1% and then work it out. I like to change the percentage into a number. So if I've got 7%, that's 0.07. And if I do 300 million times 0.07, I'll actually get the answer, and that will come out at 21 million. Okay, the hydrogen atom has a radius of 2.5 times 10 to the minus 11 meters. Determine the radius of a magnesium atom. I've seen people really overthink this. The key thing, it says use measurements, so get a ruler. If I have a look here at the hydrogen atom, okay, to me that looks like it's 12 millimeters. And if I look here, that looks to be 75 millimeters. So roughly, okay, I haven't done that perfectly, I did that quite quickly. If this is that across, the magnesium is 6 times bigger, right? Because 75, 12 getting up to 75 is that, you know, there are roughly 6 12s in 75. So I can then use that. So if the radius of this is actually 2.5 times 10 to the minus 11, then that means that the hydrogen atom we're after magnesium. Put a bit of a more on there. The magnesium, because it's 6 times bigger, is going to be 6 times 2.5 times 10 to the minus 11. 6 times 2.5 is 15. And if you remember with standard form, the number has to be between 1 and 10. So if I've got 15 times 10 to the minus 11, that actually means I've got 1.5 times 10 to the minus 10. And that's going to be our answer. Okay, next question. A student wanted to determine the density of the irregular shaped object shown in figure 11. Plan an experiment that would allow the student to determine the density of the object. Okay, so this is a required practical question. Crucially here, it's an irregular shaped object and we're after the density. If you remember density, the way we calculate it is density equals mass divided by volume. So if I want to determine the density of something, I need a way of getting the mass, and I need a way of getting the volume. And if it's a regular shaped object, I can get my ruler out and I can measure the sides of like a cube and times them all up and get the answer. But this is crucially not an irregular shape. This is not a regular shaped object, it's an irregular shaped object. So I need to be a little bit more creative with how I get the volume. Mass is going to be easy because I can just use a scale or balance. I can weigh it. I can get the mass. The volume, there's two methods. Okay, the first method is you take a measuring cylinder and you partially fill it with water. Then you plop the chess piece in, and you see here that it has raised up, and that change in volume is going to be my volume. Or you can use an Eureka can, which is a can like this, which you can fill with water, and it's got a spout. So anything which goes into here will increase the water level, and it means it will go out down the spout. And here I could put a measuring cylinder. Okay, so as I put the chess piece in, the water rises, goes down in here, and I can measure the volume. Which one you choose is up to you. I like this one because Eureka cans are fun. No other reason. So let's plan that experiment. Okay, so I'm going to start by thinking about what I need. Okay, so to actually, if I think about Rustman, okay, where this is not as rigid as Funky. The key, a key thing for here is, notice I've done all of my underlining the keywords. Think of any other keywords is things like Eureka can, measuring cylinder. Plan is my command word. Make sure you organise your answer. If I'm doing an experiment, that means I want a method. Okay, that means it's got to be step by step, nice and clear. So that's exactly what I'm going to do. I'm going to answer this in steps. So step 1, okay, is weigh the piece on a balance to obtain the mass. Now it's important we do that first, isn't it? Because if I put it in the water, some of that water is going to kind of remain on there. It's going to be wet, and that means that the mass won't be as accurate as it could be. So I'm going to weigh it first. 2, okay, I'm going to take the Eureka can, set up a Eureka can with a measuring cylinder to measure the overspill. Okay, step 3, place the piece in the can. Okay, 4 will be measure the water in the measuring cylinder. Step 5, okay, and this is where some people miss off. You are after the density, so now I've got the mass and the volume. Okay, I want to calculate density. Overwhelmingly, actually, I'm pleased that a lot of the students I teach remember about the Eureka can or the measuring cylinder, but they're so focused on that volume that they A, forget to say weigh, and B, forget to say you now use the equation density equals mass times volume to get the density. Okay, so the last step is use the equation density equals mass divided by volume to obtain the density. Okay, 2 little more subsections on the foundation paper. Another student did a similar experiment. He determined the density of 5 common plastic materials. Table 3 shows results. I've got acrylic, nylon, polyester, polystyrene, PVC, and the values there. graph questions are your godsend. Please practice your graph abilities. Okay, for this task you're going to get 4 marks. That is exactly the same, right, as that's 2/3 of that complicated method, or more marks than doing a really complicated equation. So graphs, check them, be methodical, and use one of these. So write the correct scale. I remember I was talking with Russman about answering all the question. Here's a key point. I need to write the correct scale. I need to draw the bars. If I don't do both of those, I'm going to miss out on marks. Some people get so carried away with doing the bars, they won't do a scale. So, clearly because I've got 2 bars here already, the scale has actually already been made up for me. I need to work it out. And I can see I've got kind of 2 big squares and then 4 little squares here for acrylic, and that's 1,200. Well, if I actually count the number of little squares, that's 24. So if I've got 24 little squares, I've got 1,200, and you can actually see that means that there is 50 per tiny square. Okay, 50 per tiny square. So that actually has worked out and determined my scale for me already. So this part here must be 1,000, and this part here must be 500, because that's 10 little squares, 50, 10 more little squares, 1,000, 1,500. Done. That is my scale. Draw the bars of polyester, polystyrene and PVC. So polyester is 1,380. So up to this line will be 1,000. Okay, this line will be 1,500. So I've said a little square is 50, so that means one little square will be 1,450. Oh, let's go up from 1,000. 1,050, 1,100, 1,150, 1,200, 1,250, 1,300, 1,350. And because it's 80, it's kind of going to be in between that and 400. So there is where I'm looking. Okay. Draw. Again, use a ruler up to that point. Okay, do not waste your time by colouring in. Don't need to do it. Okay, you're probably going to be stuck for time on this, so make sure you don't waste it doing colouring in. Polystyrene 1,040. Okay, so here's the 1,000 line. Again, one square would be 1,050, so it's going to be just below that, somewhere like there. Again, you can see how much better it is when I actually use a ruler, because that looked terrific. Notice how I'm following the same width of bar that they're used over here. PVC 1,100, nice round number. Okay, 1,000, 1,050, 1,100. So that's 2 little squares higher than 1,000. Okay, and there we go. Okay. The student is given a different plastic material. The student determined the density of the material 3 times, so I've got these values here. Determine the uncertainty. That basically means how much either way is it going to be. I think a lot of the time I've seen students really struggle with uncertainty. You've got 3 values here. You've got 960, 1,120 and 1,040. And if I actually average them, okay, if I average them, that means add them up and divide them by how many there are. Okay, you actually get 1,040. Now, the lowest number that I got was 80 less, and the highest number I got was 80 more. Right? So that means that my answer could, in actual fact, be 80 lower than this, and it could, in actual fact, be 80 more than this. Uncertainty really gets the heart of experiments, where you're never going to get things perfect. Okay, so if it can be 80 more or 80 less, okay, that is my uncertainty. So the uncertainty is plus, or is 80 kilograms per metres, okay, because the actual answer is 1,140 plus or minus 80. It can be 80 more, it can be 80 less. So my uncertainty is 80. And that's the foundation paper. Okay then, so moving on to the higher only questions. They start here on question 3 on the higher paper. If you see here, figure 5 shows a diver. The diver is using a canister of compressed air so that he can breathe underwater. Which two sentences describe the movement of air particles in the canister? So what this is really asking you is, what are the properties of a gas? Do they vibrate around a fixed position? No, that's a solid. Do they move in random directions? Yes, that is most certainly a property of a gas. Is the motion of all the particles predictable? Now, watch out for this, because very often in these tick box questions there'll be several points which contradict each other, because I can't tick that they move in random directions and also that the motion of the particles is predictable, because that's the opposite of random. So if you get pairs like this, just know that if you are stuck, you're not going to be ticking both of them. They move at a range of different speeds. They most certainly do. They've chucked in them, they move in circular paths thing to try and confuse you with electrons. Question 3.2. The temperature of the air inside the canister increases. What happens to the movement of the air particles? So if I increase the temperature, that means that the particles have more energy, and that energy is in the form of kinetic energy, which is the energy of movement. So if I've got more kinetic energy, more movement energy, that means that the particles will move faster. Okay, because they have more kinetic energy. Self-isolate 14 days. 3.3 says it could be dangerous if the temperature of the air inside the canister is increased by a large amount. Explain why. Again, bring it back to your real life. If you've got a canister of gas and you put it on a fire, you know instinctively that that's going to have a bad outcome. Okay, you would know that hopefully if you put a can of compressed air or gas or a can of deodorant or something like that on a fire, eventually it will explode. So we've got to think, why might that be the case? So if I think back to the last question where I said that the particles move faster, okay, if the particles have too much energy or have and move very fast, okay, they're going to be banging all over the place. Okay, they're going to be bouncing off each other, bouncing off the walls. This means they will collide with the walls of the container. Okay, that collision with the wall, okay, has a very special name, and that's pressure. Okay, so if I'm increasing the temperature, that means I'm going to get an increased pressure, and if that pressure and force on the outside of the container is too much, the container will explode. So this is an increased pressure. Yeah, so if I read back this, okay, if the particles have a large kinetic energy and move very fast, this means they'll collide with the walls of the container much harder, okay, or more force. There's an increased pressure and could cause an explosion. Okay, I don't think that was the best answer there, but hopefully you get the point. A canister of air was tested to find out how the pressure changed when it was used by a diver. Air was allowed to escape from the canister. The pressure of the air in the canister was recorded every 5 minutes for 80 minutes, and I've got this graph here. Estimate the atmospheric pressure. So if you think about it, if I have a container of air and I have the particles in here all over the place, okay, bouncing off the walls, that's the pressure. If I open the container and the air comes out, okay, or slowly you're breathing it, the end point will be where the particles inside have got the same pressure and distribution as the outside. That's the atmospheric pressure. So when it says estimate the atmospheric pressure, okay, we're looking for that point where the pressure is equalised with the outside. And if you have a look at the graph, we start off, we slope down, and then it reaches this flat line. If I read this back across, you'll see that it's one little square up. Looking at my scale, that will therefore mean 0.1 megapascals. Okay, that is actually atmospheric pressure. What we commonly call as 1 atmosphere. Divers can safely stay underwater until the pressure of the air in the canister has reduced to 25% of its original value. Determine the maximum time the diver can safely stay underwater. So if we have a look, the starting pressure of the container is 2.25. Okay, so 2.25 megapascals. 25% of its original value will be a quarter. So that will be 0.5625 megapascals, or roughly 0.56. If I now look at the graph, I'm looking at the point where 0.56 is, so that's roughly going to be between 0.5 and 0.6. I'm going to use a ruler here. I started doing it freehand and you realise how much worse it is. And I read down. Okay, so 0.56 megapascals coincides with a time here. That's between 20 and 30 minutes. That'll be 22 minutes, 24 minutes, 26 minutes, probably about 27 minutes. So that's reading off the graph. Often when you've got a graph like this, okay, use it, read the graph. What happens to the volume of the air when it is released from the container? So if I've got, if I go back to this little rubbish little sketch over here, if I've got the particles contained in a high pressure, if I equalise that pressure, if I lower the pressure, those particles must spread out because I've got a fixed number of particles. So if I'm cramming them in a certain area, that means a high pressure and a low volume. If I lower the pressure, that must equate to a higher volume. So the volume of the air increases. Okay, question 4 on the higher paper. The Chernobyl disaster was a nuclear accident that happened in 1986. Radioactive isotopes were released into the environment. The radioactive isotopes emitted alpha, beta and gamma radiation. What is an alpha particle? If you were watching the foundation questions, you'll see that I did talk about them. But an alpha particle is often called a helium nucleus. Doesn't mean that it comes from helium. Actually, helium does tend to be alpha particles which have slowed down and acquired electrons. But the reason we call it helium nucleus is because if we look at the middle of a helium atom, we tend to find 2 protons and 2 neutrons. It's just, that's all it is, 2 protons, 2 neutrons. Okay, now if you think about it, they've been a little bit more coy here with the examples. Protons are positively charged, so they have a charge, and neutrons have no charge, so they're neutral. So the answer would be this one, 2 charged particles and 2 neutral particles. Which statement about beta radiation is true? So beta is an electron moving fast. It's a bit weird, okay, it's an electron not from the outside but actually from the nucleus. You don't need to worry about how that comes about, but we often just talk about it as an electron from the nucleus. So let's think about which ones of these are true. It's not actually the fastest type of radiation, that is gamma. Gamma is an electromagnetic wave. Okay, and if we think about the electromagnetic spectrum, that means that travels at the speed of light. Because it is an electron, however, it is the type of radiation with negative charge. Which statement about gamma radiation is true? Okay, it's not a low frequency. Gamma is actually super high frequency. Okay, if you remember the electromagnetic spectrum, where we go radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. Okay. Okay, gamma rays has got the highest frequency. Okay, that means the most waves going past each second. It causes the charge of the nucleus to change. It doesn't have a charge, gamma, so that can't happen. It causes the mass of the nucleus to change. Again, doesn't have any mass. Okay, it just comes from a change in energy state. It has a very long range in air. That most certainly is the case. Okay, because it has no mass, because it moves really fast, whilst it causes the least damage of the of alpha, beta, and gamma, the least ionising. Again, that doesn't mean it's safe, but it's the least ionising. It will travel quite a long way before it's stopped by something. So that means it's got a very long range in air. Okay, continuing with the Chernobyl question. Table 3 shows 2 half-lives. Cesium-137 has got a half-life of 30 years. Iodine-131 has a half-life of 8 days. A soil sample was taken from the area around Chernobyl in 1986. The soil sample was contaminated with equal amounts of cesium-137 and iodine-131. Explain how the risk has changed. Okay, so the key term here is half-life. Okay, that is the time it takes. There's 2 separate definitions, but I'm going to kind of combine them into one. The time it takes for the radiation level to halve. Okay, it could be the number of what we call the activity of the sample, or it could be the actual number of nuclei. They're both the same definition, right? It's the time it takes the radiation to halve. I've actually been to Chernobyl, and you get more radiation on the flight there than you do there now. Okay, so, and that's all to do with the time. If iodine-131 has got a half-life of 8 days, that means 8 days after the accident, the level of radiation caused by iodine-131 is half. 16 days is halved again to a quarter. Another 8 days to an eighth, and so on and so forth. If you think about it, in 30 years, that has gone through, okay, or between 1986 and 2018, which is 32 years, it has gone through so many of those half-lives that it's declined to almost nothing. Okay, technically there will still be a little bit, but it's pretty much nothing. Whereas cesium-131 with a half-life of 30 years will have only gone through one half-life. That means the level of radiation from cesium-137 has basically halved once. So the level of radiation from that today is only half of that the accident 30 years ago. So clearly now cesium-137 is the more dangerous of the two because there's more of it left. Okay, so explain how the risk linked to each type has changed. Okay, iodine-131 risk today is very low because over 32 years it has gone through very many 8-day half lives, so the level is effectively 0. Notice again, I've dealt with that. I'm now going to do another paragraph. That structure, that clear process to your answer is really important. So cesium 137 risk, however, is still high because it has only passed one half-life, and so the level of radiation and risk is basically halved. Okay, question 4.5. Determine the year when the activity of cesium-137 in the soil sample will be 1/32nd of its original value. So again, thinking about half-life. If I go through one half-life, I will have half of the original value. If I halve again, a quarter, an eighth, a 16th, and a 32nd. So let's think how many times that's halved. It's halved once, twice, 3 times a lady, 4 and 5 times. So that means that it has undergone 5 half-lives. Okay, we've told in the question that the half-life of cesium-137 is 30 years, so therefore the time is 5 times 30 years, which equals 150 years. Now, there's one more thing, okay, because I know, and I was tempted just to write the answer there as 130, but it's the year. Okay, Chernobyl happened in 1986. Okay, so I want to say 150 years after 1986. So that will be 2036 plus that 2136. Okay, so the year 2136. The level of radiation from cesium-137 will be 1/32nd of its original value. Okay, question 5 is looking at cavity wall insulation. You can see it's got a diagram here. Explain how the wall reduces unwanted energy transfers. Okay, so the way of transferring heat, there's 3 ways. Okay, there is conduction. Okay, there is convection, and there is radiation. Okay, so conduction is the method of transferring heat basically through a substance. Okay, if I take a metal rod and I heat up one end, okay, the heat moves through the metal, okay, and warms up passing through the metal. Okay, that is conduction. It's the movement of hot to cold through particles. Convection is only in a liquid or gas. Okay, and this is the flow, not the most technical way, the flow of or the movement of heat through the movement of particles themselves. So for instance, if I have a fire here, okay, the particles here, so say this is in air, the particles here will get hot. That means that they'll expand. Not the particles themselves, okay, you'll get a higher volume. If I get a higher volume, that means the density's gone down, and that means that the hot air rises to the top. We often talk about hot air rising. So the hot air rises to the top. As it gets there, okay, it will transfer the heat to the particles up here and cool down, and that means that the particles will come closer together, the density will increase, and that means that it will now sink to get heated by the fire again and rise and sink and rise and sink. This is what we call a convection current. Okay, so this is actually how radiators work. I know we're talking about radiation here, but radiators actually work by convection, by having a hot surface which heats the air and moves through the room and heats up the room. Radiation, what we're really talking about here is infrared. Okay, this is the idea that hot things give off an electromagnetic radiation. Things which are black emit it really well, and absorb it really well. Things which are white or shiny will not emit infrared really that well at all, and they'll also absorb it the worst as well. So let's think about how cavity wall insulation is going to affect it. If I didn't have that insulation there, I essentially have a row of bricks and a row of bricks, and there is air. Okay, so the first thing it's going to do is it is going to eliminate the gas from that. So that means that I am going to severely reduce convection. So cavity wall insulation, okay, replaces the air preventing energy transfer by convection, which cannot occur in solids. Okay. I think the other big impact here is going to be on conduction. You're making it have an insulating material. That means that within the material it's going to be bad at transferring heat from one end to the other. Okay, that is going to be slow in an insulator. A conductor, for instance, like metal, okay, that is very fast. Okay, so that's a conductor and that is an insulator. So because this material is an insulation, that means that conduction will be reduced. Okay, as it is an insulating material, it will transfer energy by conduction poorly. You could mention about radiation, but I think these two are clearly going to be the more important. Okay, the cavity wall insulation was tested. The heating inside the house was switched off. The temperature inside the house was measured every 20 minutes for 2 hours. Table 4 shows the results. So you can see it started off at 25 and it cooled down. Determine the temperature rise inside the house after 30 minutes. So at 20 minutes, it was at 20.08, and at 40 minutes it was 17.4. Okay, now this isn't going to be accurate, especially because it's not going to be a linear distribution. I mean, it's not going to be a straight line, it's a curve. But an easy way to determine at 30 minutes is just to find the halfway point between these. So 20 minutes is 20.08, 40 minutes is 17.4. So the difference between them is 3.4. So because I'm after 30 minutes, okay, 3.4 divided by 2 is 1.7. So that means I could either add 1.7 to this or take away 1.7 for that. The halfway point between them, okay, is 19.1, because that is 17.4 plus 1.7. Okay, that's not going to be completely accurate, but it's a good rule of thumb. Okay, figure 8 shows the gas boiler used to heat the house. Describe how different energy stores are changed within the boiler. Okay, this is where we need to go really on it with our technical terms. Think about our energy stores that you've probably done to death actually throughout your school experience. What type of energy is in the fuel? That is chemical energy. When I heat it, okay, it is going to be transferred to thermal energy, which is essentially just the kinetic energy of the particles. So that thermal energy is going to increase the thermal energy of the cold water, and I've said that in reality that is kinetic energy. That hot water, okay, is going to heat the gas, so that's transferring thermal, and because it expands really hot gas, that is kinetic. So overall, really, okay, we've got chemical to thermal to kinetic. Okay, so the chemical energy of the fuel is transferred to thermal by combustion, because that's the fancy word for burning, that's what we're doing. The thermal energy is transferred via the water to the air. This increases the kinetic energy in the air/gas. Okay, to heat the house, the boiler transfers 15 megajoules of energy in 10 minutes. Calculate the power of the boiler. Write the equation that we're going to use. So this is our first higher only use of funky. So we need to write down the formula. Okay, this is going to be in the form of power equals energy divided by time, which in symbols is P equals E divided by T. Units check. Right, we can see here we've actually got some weird units. We've got megajoules and we've got minutes. We need to make sure we convert them both. So 15 megajoules. Whenever I see a capital M, the mega, okay, think about million, right? The M standing for million. So if I've got 15 megajoules, I've got 15 million joules. So that's going to be 15, 1, 2, 3, 4, 5, 6. If I've got 10 minutes, well, there's 60 seconds in a minute, so that means I've got 600 seconds. That is my units check done. It's very important you do that. If you forget it and you use the numbers, as long as you put them in the equation, you will get some marks. But to really get those full marks, this is why this is a 4-mark question. Okay, I think you need to remember that units check, converting the units. So N, numbers in. So looking at the equation, I've got E divided by T, so that's going to be 15 million divided by 600. Okay, and if I work that out, hey Siri, what's 15 million divided by 600?
15 million divided by 600 is 25,000.
Thank you. Again, always use a calculator. And then why you don't forget the units of power are watts. So that gives us 25,000 watts. Does that make sense? I think so. Okay, you are boiling a lot of water. That's an intense process. So it makes sense that it will be quite a high number. Okay, question 6, which I think might be the last question on the paper. It is indeed. Okay, a student built a circuit using filament lamps. Sketch the current potential difference graph for a filament lamp. Okay, back in the previous paper, okay, we had to investigate the graph for a device which follows Ohm's law. We call it an ohmic resistor, which is something like a wire, and we talked about a straight line. That is not the case for a filament lamp. And the reason it's not the case for the filament lamp is a filament lamp gets hot, and because it gets hot, that means the resistance increases. Why is that the case? If I look at the structure of a metal, okay, I have rows of positive ions, okay, amongst a sea of negative electrons. And when I conduct electricity, these electrons move through the material. If I increase the temperature, these ions are going to start wiggling about, okay, and they're going to bump into the electrons as they move through. That offers some resistance to those electrons flowing through the metal. So that means an increase in temperature means an increase in resistance. So as I dial up the potential difference, what I referred to earlier as the push through the circuit, that means that even though I'm pushing harder, I'm getting more of a pushback from the wire, from the filament bulb, and that means that less, it's not going to go down, but there's not going to be a noticeable increase in the current, the flow through the circuit. So even though I'm giving it more of a push, I'm not getting as much of a reward in the current. So it will go up, but it will slow down like that, okay? And the opposite is true in the opposite direction. So we get this kind of S shape, okay? Because I'm giving it more of a push, but I'm not getting as much of a reward from the current because of that increased temperature and the increased resistance. Figure 10 shows a circuit with two identical filament lamps. Compare currents 1, 2, and 3. Okay, they're identical. That means they've got the same resistance. Okay, so what does that mean? It means that one path is not noticeably easier than the other. So you can see that the current is coming out here and it has to split into two paths. This is a parallel circuit because I've got two, each component has its own loop. Okay, I've got different loops. The opposite, remember, is a series where I have one loop, and that is not the case here. In a parallel circuit, okay, the current is shared. Okay, it's shared between the paths. So if I have to compare them, I've got this current here splitting into two identical paths. So that means that the current here will halve between here. So I1 is double I2 and I3. Okay. Think about it like this. Okay, if I have a motorway with two lanes of traffic and it splits to go around, say, like an obstacle, right? This is a really bad example. And I join back up again. Okay, half the cars will go that way, half the cars will go that way. So if I compared the amount of cars going through the road here and here, okay, it's going to be half. So I1 is double I2 and I3 because in a parallel circuit current is shared as the bulbs are identical. The current will halve. Okay, calculate the charge that flows through the cell in 1 minute. Each filament lamp has a power of 3 watts and a resistance of 12 ohms. Write any equations that you will use. The other big flag here is it's 6 marks. Okay, these are the hardest equation questions at GCSE. They require multiple equations and you really need to be able to work your way through and be really logical with it. So I'm going to bring up Funky again, and that's just simply so we can keep track of what we're doing, so we don't get ourselves in a muddle. If we follow this, we're not going to be moving numbers all over the place. So let's think about what formulae I'm going to need. Calculate the charge that flows through the cell in 1 minute. So I've got charge and I've got time. Okay, so if I can think about an equation which has charge and time in it, well, that will be Q equals IT. Charge equals current times time. But I crucially don't need the current. I don't know the current. But what I do know is the power and the resistance. So I need to think of an equation which has got power and resistance in it and current. And that will be P equals I squared R. Okay, so what I can do is I can use this equation to get I, and then I can put that I into the equation, and then I can get charge. So the first formula I'm going to need is to use this one, okay, to then help us generate this. Now, we haven't had to do it yet, but I'm going to rearrange the formula. If you find that difficult, you can actually just put the numbers into the formula as it is, and work it through that way. I like to rearrange it. I think it's just the way my brain works. I'm a little bit more algebraic like that. So if I'm after the current, I want to get it in the form I equals, and that makes all of my numbers nicer. So if I've got P equals I squared R, if I divide both sides by R, that means that I squared equals P divided by R. And then because of that squared, that means that I equals the square root of P divided by R. So let's put that up here. So let's do my first equation. Formula. I equals the square root of P divided by R. Okay, so my power is 3 and my resistance is 12. Units check, watts, ohms, perfect. So that means that it's going to be the square root of 3 divided by 12, which is the square root of a quarter, which actually, if you know your surds from maths, is the square root of 1 over the square root of 4. You don't know, just put it into a calculator if you're not sure, okay, but I'm just showing you that is the square root. The square root of a quarter is a half. Or to think about that the reverse, half times a half is a quarter. So I know that the current is a half, which is 0.5 amps. Okay, so that's quite a long calculation, and I've got my units. You don't have to worry about them too much really. Really, that comes at the end. But my current is 0.5 amps. So now I'm going to use my second equation. Q equals IT. That's my formula. Units check. That's in amps. Fine. That time is in a minute. Is a minute. So 1 minute, okay, is 60 seconds. Remember, it has to be in seconds. Now I'm going to put my numbers in. So it's going to be 0.5 times 60. And that is therefore going to be 30 when I calculate. You don't forget the units. The units of charge are coulombs. So putting it all together, I've used two equations, worked them through, and got the answer 30. Okay, this last question. The student builds a different circuit. Figure 11 shows the circuit. Okay, I've got an ammeter here. Okay, I've got a regular resistor. I've got this here is a light dependent resistor. Okay, what does that mean? Well, it means that as the light increases, the light intensity increases, the resistance actually decreases. And I've got a voltmeter. Okay, so it says explain how the readings on both meters change when the environmental conditions change. So if I'm again going to look at Russman, this is again another example of where all of the question comes in. Okay, I've read the question. The command word is explain. So that means I've got to say what's going to happen and then give a reasoning, okay, a logic behind it. Keywords or subject words in here are the meters and the environmental conditions. Okay, you've got to think about what those environmental conditions are. Because this is a light dependent resistor, those environmental conditions is clearly going to be light. That's the one we're worried about. Subject keywords, I know that it's an ammeter, I know it's a voltmeter, and I know that it's a light dependent resistor. These are our key subject keywords. Any other keywords? I think we're going to need to be mentioning Ohm's law here. Okay. Ohm's law is V equals IR. Okay, so we can think about how the relationship between the resistance, current, and voltage changes. And the other thing is the idea of resistors in series. Okay, that they add. Okay, so the total resistance is the resistance of the first plus the resistance of the second, so on and so forth. And make sure you organise your answer. I'm actually going to take this kind of in two halves. I'm going to look at the voltmeter and the ammeter separately, because if I'm going to answer all the question, I have to talk about both meters. So, what's going to happen? Right, let's think about this. If I increase the light, right, so if the light intensity increases, the resistance of this is going to go down. given that resistors in the series add up, okay, that means the resistance of the whole side here is going to go down. Okay, that means the resistance of this whole bit is going to go down. So if I'm looking at the ammeter, the resistance here has gone down because the voltage out of the battery is not going to change. So this is going to be, if that is the same, and this is now lower, okay, if that means that the current must be higher to balance it out, okay, because if this is 6 equals, right, and it was 6 equals 3 times 2, and this has now gone down to 1, that means that the I must go up to 6, okay, just to write that down. It's a bit of a numbers thing. Okay, if that number has gone down to 1, that means that this number's got to go up to still make it equal 6. I've just picked those numbers just to try and help it make sense to you. Sometimes it is worth just picking some numbers, sticking them in. It might help it like logically process for you. So in terms of the ammeter, if the light intensity increases, that means that the reading on the ammeter will go up. Okay, that means there'll be more current in the circuit. Let's think about this voltmeter, because this is a little bit more complicated now, because this voltmeter is not over the whole lot, it's over this resistor in particular. And it comes back down to this resistors in series. This is a fixed resistor. Okay, it's a fixed resistor. So, if I think about Ohm's law again for this resistor, I've already established that the current will go up. So if this is the same, the resistor is the same, and this is higher, okay, the I is higher, that means the V must be higher. So I've got a same number times a higher number, so that V must be higher. But the voltage coming out of the battery has got to be the same. Okay, the battery is just sat there producing a certain amount of voltage potential difference. So if the voltage here is higher, if those two are going to add up to be that number, okay, if these voltage in series, remember, adds up, okay, if these are going to add to make that, that means that if this is higher, this must be lower. So the reading on the voltmeter will go down. So to summarise before I write it down, the reading on the ammeter will go up. Okay, you can think about this as the resistance has gone down. So that means that for the same push, I'm getting more of a flow through the circuit. And the reading on the voltmeter will go down. Okay, for the reasons that the voltage across here must add together to be the same as the battery. Voltage going through here is going to be higher, so therefore the voltage going through there must be lower. Okay, so the first section of the answer really has to address the fact that there's a light dependent resistor. Okay, the circuit has a light dependent resistor. This means that its resistance will decrease if light intensity increases. Okay, and this is actually how streetlights work. It was actually one of my dream jobs as a kid, is I really wanted to turn on all the streetlights because I thought they were switches, and then I realised that light dependent resistors and sensors are a thing. Very disappointed. So if I'm then considering here, okay, I'm going to consider the ammeter. So the ammeter reading will increase. Okay, this is because they will increase if light intensity increases. This is because the total resistance in the circuit will decrease as the battery / cell voltage is the same. Ohm's law means the current will increase. Okay, notice how I'm not actually doing any fancy sentences. I think it's really easy to come out of history or English and try and do really elaborate sentences. In science, you don't need to get complicated. Just go, this means, this is because, bosh, bosh, bosh. Okay, so last thing, remember to answer all the question. Okay, the voltmeter reading will decrease as light intensity increases. Another way to think about that is if the resistance has gone down, it requires less push to get the same current through. That might also help in your mind. Will decrease as light intensity increases. This is because the resistance this is because the current increase let's go with resistance. The resistance decrease. Okay, if you think about it, if R goes lower, then V must go lower for the same current. This means this because the resistance increase means a decrease in voltage. Now, that question is super hard. I think electricity is one of the hardest topics out there. I don't think I fully understood it until I actually started teaching it. I could do all the equations, I could argue all the points, even through uni. I never really thought about it, and I could never really get my head around it. So if you find that particularly complicated, it is. Okay, this is a question where if you are getting close to 6 marks, you are a grade 9 student. This is hard. Okay, so don't be disillusioned. But that is the 2018 physics paper 1. I hope that you found that useful. I expect that it will obviously become more useful around exams or mocks if you've got them coming up. Probably not that much of a use right now, but I'm sure you might find it useful in the future. Anyway, thank you.